Okay, so the recording has started. Let me give you a moment to to copy the example down. Okay, so we want to find, in this problem, we want to find the critical numbers of this interesting function, f of x equals x to the negative second power times the log of x. So how do we find, class, how do we find the critical numbers of a function? How do we find critical numbers for a function? That's right, Ian. We look for where the derivative, the first derivative, equals 0. That's where we look. So, all right, and I'm trying in the lectures to do. I mean, the book has examples where, like, they'll work with a polynomial, and they might have another function, a different type function. I'm trying to work with functions that are, interesting in a sense, because we're using calculus to help us understand the behavior of functions. And even if you graph the function on your calculator and look at the function with your eyes, you can't always see the true behavior of the function, the in-depth behavior, I should say. So, all right. Well, we're gonna take the derivative of this function. Okay, so of course we're going to use, well, here's the derivative. What rule did we use there to get the first derivative? Good, Zoe, we used the product rule. Good, Joe, the product rule. Okay. All right, so we use the product rule. We use the product rule. And again, what I'm interested in is finding out where this first derivative equals 0, where the values that it equals 0 at. So we want to do this analytically, okay, if we can, and this we can do analytically, and that means that we want to use math to find out where that first derivative equals 0. And so the way I'm doing this problem is the way I would expect you to do it on your exam next week. Okay, so we want to find out the values of x for which f prime of x equals 0. Well, when the first derivative is in this form here, it's difficult to find the x values where that first derivative equals 0. So what we do is we say, okay, well, we have a negative exponent here, x to the negative 3. Let's write it as x to the positive 3 and bring it to the denominator. Okay, and then x to the negative second times 1 over x. Well, 1 over x, of course, is the same as x to the negative first. And x to the negative second times x to the negative first is x to the negative third. So we have the sum of these. We have the sum of these two functions here. And what we want to do is bring the functions together, combine the functions. Okay, well, we want to add the functions. But to add the functions, I need to have the common denominator. X to the negative third I write as 1 over x cubed. And this allows me then to write the first derivative as 1 minus 2 times the log of x over x cubed. Okay, and this here is a form that we can work with. That's a form that we're able to work with. Okay, are there any questions? Joe says BRB. I'm not sure what that means. Maybe cool. I don't know. Oh, be right back. Okay, all right. Thank you, Rodrigo. Well, it's on the recording. It's on the recording. Okay. If I want to find x values for which well, hold that thought, Ian. Hold that thought. Hold that thought. So where, like to find out where the derivative equals 0, is my focus going to be on the numerator or the denominator? The numerator, right? I don't want the denominator to equal 0. I mean, well, what I'm saying is, if I'm trying to find out where f prime of x equals 0, okay, and I will make just one comment here, one quick comment, one moment, because yeah, Ian did mention, and he's right on this, a critical number of a function, okay, and that's what we're looking for, the critical values. A critical number of a function is a number c in the domain of the function such that either the derivative of the function at c equals 0 or the derivative of the function at that c value does not exist. So we do have to consider both cases. That's right, Ian. Right now, we're looking at where the first derivative equals 0, and clearly, the first derivative would equal 0 when the numerator equals 0. So 1 minus 2 times the log of x equals 0. That would occur when 1 equals 2 times the log of x, or a half equals the log of x, and then that means then that e to the half equals x. So if you take, like for the, maybe add a little step in here. So we're right here, and if you exponentiate both sides, you remember doing this in pre-calculus, right? I have 1/2 equals the log of x. So that means that e to the half would equal e to the log of x power. But e to the log of x power, the exponential function and the natural log function, are inverses of each other. So that's just going to get you x. How many remember doing exponentiation in pre-calculus? Okay, all right. Joe remembers it, and we're using it here. Okay. Are there any questions so far? Okay, well, then let's go. So now we found one critical number. X equals e to the half is a critical number. But again, remember, to get that, we had to write our first derivative as a fraction. We have to get it in a form where we can analytically find these critical values, critical numbers. Okay, so let's go to the next page then. X equals e to the half is a critical number because f prime of x equals 0 when x equals e to the half. But now the other critical numbers that we need to find are where this first derivative does not exist. And clearly, well, here's your first derivative, right? And how do we determine where the first derivative doesn't exist? Do we look to the numerator or to the denominator? So f prime of x is equal to 1 minus 2 times the log of x divided by x cubed. Okay, Yaki, good. So what can't the denominator equal? What can it equal? Can't equal 0. So that means that f prime of 0 does not exist. But here's the thing. You might say, oh, okay. Well, x equals 0 is a critical number. 0 is a critical number because the derivative does not exist at x equals 0. But keep in mind that 0 is not in the domain of the function f of x equals x to the negative second times the log of x. That was our function, right? Why isn't 0 in the domain of our function? So again, I can write the function as the log of x divided by x squared. And yes, so the log of 0 is undefined, definitely. And also, you can't have 0 in the denominator as well. So therefore, the only critical number is going to be the square root of e. That's the only critical number. Square root of e is equal to e to the half, right? So you have to be careful in your exercises. I mean, they are free response. I think most all of them are free response. But you have to be careful before you just, put in, like, state an answer, because, well, you have to be careful. Because, like, for the exam next week, for a free response question, you have 2 tries. And you just have to be a little careful before, So you might think, oh, well, again, you might put in say you have 2 critical numbers, e to the half power and 0. But 0 is not a critical number because 0 is not in the domain of the function. Okay? It's like it's not even up for discussion, Critical number has to be in the domain of the function, right? All right, are there any questions on that? Any questions on that? All right, are we ready to move to the next problem? All right. All right. Okay, very good. John's good. Well, let's move forward then. Let's look at another problem. Now here we're going to find the absolute maximum and absolute minimum values of this function. Okay, so take a moment to copy it down. Copy the example down. And by the way, we're restricting the function over the interval -1 to 4. Okay, so we want here. So the past several examples, we looked at finding critical numbers of a function. Okay, now we're looking to find where the function has an absolute maximum and an absolute minimum. Okay, and we have this interesting function, f of x equals x times e to the negative x squared. Well, f of x equals x times e to the power negative x squared over 8, and we're restricting ourselves, we're restricting x to be between -1 and 4. Okay, so, well, let's go ahead here. What do we have to do? You know, I mean, a function, right? A function. I want to be a little careful how I phrase things here. I think, you know, just in of like I don't know what this function looks like. Okay, I don't know what it looks like, but I'm just thinking in my mind of, hey, a function, you know, I draw some function, a function, okay, might look like this, right? Function might look like that. Well, actually, hold on. If I restrict the interval over which the function's defined, if I restrict the interval over which the function's defined to say go from a, and that's, I'm not saying that this function here, f of x equals x times e to the negative x squared over 8, I'm not saying that's what this function I'm drawing here up here looks like. But let me just show you what I'm getting at here. Hold on. Just give me one moment here. Okay. So, you know, maybe, all right, so maybe the function looks like this, and I'm closing the endpoints. Okay, So we're including the endpoints here. So I mean, for what would I have to look at? Well, let me ask you, for this picture. Hey, so somebody's don't draw, please, on my thing. So there's a reason I have it the way it is, okay? Get some crayons and a sheet of paper, you know, and if you want to draw, but please don't draw my picture. All right. So, I mean, let me ask you this. Okay? Hold on. I'm gonna change this a little bit. It'll be worth doing. Hold on. Let me just. Trying to rather than us just, you know, do things in calculus, I want to tell you why we do those things. Okay, so I have this a graph of a function. I'll call it a function g. Okay, and it's some kind of polynomial. And is there a maximum? Is there, and I'm restricting the polynomial to be between a and d. Okay. Just like here, I restricted this interesting function to be between -1 and 4. So for this function g here, is there an absolute maximum for that function g? Is there for this function g? Okay, what value of x does the absolute maximum occur? Good, everybody. It occurs at x equals b. Okay, at x equals b. Now, how would I, but you know, there's a saying, your eyes will fool you every time. We say that in statistics, that's a saying. You know, if I wanted to find that value of b, what would I need to do to my function g? What would I need to find? I have this function g of x. To find out the value of b, okay, I mean, we know the absolute max occurs at b, but what's a way to verify that a maximum occurs at x equals b? And okay, Goodians, take the derivative of g prime, set it equal to 0, and if you set it equal to 0, I mean, you know, why do we do that? Because we know that the tangent to the function g of x at x equals b is flat, so it has slope 0. So x equals b. That's how we could the derivative g. I guess what I'm saying is this. Hold on here. Hold on. G prime and we're having a little trouble today. I'm sorry. This is just give me a moment here. I'm going to make sure my work's nice, you know. So g prime of b equals 0. So certainly, if we were to identify maxima, is there any other point? Is there any other x value where the derivative of g equals 0? based on this picture up here. Good. G prime of C. Good, everybody. Good, Ian, Sebastian, and Zoe. G prime of, and John, G prime of C equals 0. Rodrigo, absolutely. So, you know, if I'm looking then to find, and we notice that at x equals C, we have an absolute minimum as well. So here, x equals B and x equals C, those values of x, but x equals B, the function g of x here has an absolute maximum. So at x equals B, the function g has an absolute maximum. At x equals C, the function g has an absolute minimum. Okay, by the way, does the function g have a local maximum at x equals B? I mean, we know the function g has an absolute maximum at x equals B, but is x equals B, does the function g have a local minimum, a local maximum as well at x equals B? Well, let me clarify here. Let me clarify. Let me clarify. So we agree. Let's just focus on x equals B. We agree that this function g here. We agree that. Hold on. Let me go to the whiteboard here. I think it's worth doing. Okay. So I'm just redrawing basically the picture that we had. Okay. And this will be in the report. So let's focus on B. When x equals B, g prime of B equals 0. Okay. So we know that there is we know that there's either a maxima or minima at x equals B. Well, based on the here, we can see that x equals B would provide a maxima. So g of B is a maximum. But g of B, it's an absolute maximum, but it's also a local maximum, because around a neighborhood of B, the function g is highest at x equals B. So I tend to like to think of x equals B, g of x has a local maximum, but hey, it also happens to be absolute maximum. That doesn't always happen. Okay, that isn't always going to happen. But at x equals C, we know at x equals C that g prime of C equals 0. So there is at the very least a local minima at x equals c. And if I put a little neighborhood around here, around x equals c, I can see, you know, I'm drawing a horizontal tangent there. I can see that x equals c, there's a that G has a local minima at x equals c, but it also happens to be an absolute minimum. Okay, but the point I'm trying to demonstrate here, is that in order to find these absolute maxima and absolute minima, we have to take the derivative of our function. Okay, we have to. Now, sometimes what will happen is you can have a situation like this. Okay. Actually, hold on. Let me just. No, let's not do that because we're working with a problem where we have a restricted interval. Okay, but like for instance, you could have a function where the function does this. Okay, it does this and this and this, and here at, let's say this is like some point B here. Okay, for this function, I'll call it function f, is at x equals b, is this, I mean, is there a minimum or maximum of the function at x equals b? Is there a minimum or a maximum? It's a minimum. Is it an absolute minimum? Here, I'll change the function a little bit there. Does x equals b have an absolute minimum? No, it's not an absolute minimum because the absolute minimum occurs here at d of the function. That's, assuming the function, goes up forever there. Absolute minimum of the function occurs at x equals d, but x equals b would be, it is a minimum. It's just, there is a minimum there. It's just why a minimum? It's not an absolute minimum. It's a local minimum. Good. So does this help you see the difference? Does this help you see the difference? Is this helpful? Good, good. All right, wonderful, wonderful. So in an absolute, an absolute minimum, absolute maximum does not have to be a local minimum or a local max. And you'll see this in the example here. So it's in the recording. Let me go back to that example now. Sometimes, you have to just kind of, I felt a little more instruction was helpful. So now back to the example at hand. We want to find the absolute minimum and absolute maximum values of this function, x times e to the negative x squared over, sorry, the function is equal to x times e to the power negative x squared over a. And we understand now that in order to find maxima and minima, even absolute max and absolute minima, we have to consider taking the derivative. So that's what we're going to do. That's what we're going to do. And so here we go. Here we go. So we are taking the derivative. And what rule did we use here? We used two rules, actually. What rules did we use to take the first derivative? Got the chain rule involved, and also that's right, so what other rule? The product rule, that's right, Ian. So we take the first derivative, and that gets us here. Okay, let me know if you have any questions. All right, so now is this form here, the circle, so the derivative, I, wrote it a little bit nicely, a little bit nicer there. But is that going to be analytically good enough to find out, to find absolute maxima, absolute minima? In other words, I want to, well, in order to find that, remember, I find out where that first derivative equals 0. Is this form here, circled in blue, going to be adequate to find those particular x values? No, no. We have to get it. That's right, Bitsur. That's right, Lynn. We need to get it in factored form. We need to get it in factored form. I can't have the difference of two functions. I gotta have one function in nicely factored form. So what I'm going to do is, oh, well, there is a common factor here, isn't there, between the two terms? There is a common factor. So let me factor that term and write the first derivative this way. All right. Now this here, this way of writing the first derivative is going to yield us fruit. Okay, it's going to yield us fruit. Because now I can find the x for which the first derivative equals 0. I can do that. So for the first derivative to equal 0, remember, we have two factors, e to the negative x squared over 8 and 1 minus a fourth x squared. We have two factors. Okay, so we want to know then when does the product of those factors equal 0? Okay, I want to make sure I'm pacing myself all right. Are there any questions? All right, well, so the e to the negative x squared over 8, can that factor ever equal 0? Like for any x, can that factor ever equal 0? No, it can't. So that means then that the values of x where the first derivative equals 0 have to come from the second factor, 1 minus a fourth x squared. Okay, so if the product of these two functions equals 0, this implies then that 1 minus a fourth x squared would equal 0. Because the other factor, e to negative x squared over 8, that'll never equal 0 for any value of x. Are there any questions? Try to be careful. You know, it's easy to get kind of hung up in the terminology. We don't want to get hung up in the terminology. Okay, well, let's go ahead to the next page then and solve for x. So again, I'm focused on solving 1 minus a fourth x squared equals 0. If that's the case, then 1 equals a fourth x squared. And if I multiply both sides, of this equation by 4, we'll get 4 equals x squared. So x equals plus or minus 2. And I think I left a little something out here. One moment. I mean, we're good so far, but here, since x equals -2 is, I want to insert this, x equals -2 is not in my interval from -1 to 4. Right? We're restricting x. We're restricting our x values that we're considering, the domain, we're restricting our domain to be x values between -1 and 4. So since x equals -2 is not in the interval from -1 to 4, we exclude this value from consideration. And so then we consider x equals 2, but also for absolute minimums, absolute maximums for these extreme values. Remember, we have to consider also the endpoints, because it's possible that the function might take on its greatest value at one of the endpoints. Okay, so any point, any x value, any x value. I'll say it's the right way. Well, yeah. Let's just continue here. So we have to consider evaluating the function at our endpoints and evaluating the function at x equals 2. And what we're going to do is evaluate the function at our critical number, x equals 2, and evaluate the function at our two endpoints, x equals -1 and x equals 4. And then we get our answers, and then based off of the answers, we can determine what the absolute maximum and absolute minimum values of the function are over the interval -1 to 4. Are there any questions so far? Now it's just basically, now we can answer the question. So the largest value here is 1.21. and that's at x equals 2. So f of 2, which is equal to 2 times e to the negative a half, which is 2 over the square root of e, which is approximately 1.21. That's an absolute maximum. And then the smallest value is negative 0.88. Okay, that's the smallest value the function takes. So that means f of negative 1, which is negative e to the negative 1/8 power, which is the same as negative 1 over the 8th root of e, which is negative 0.88 approximately. That's going to be your absolute minimum value. Okay, are there any questions? And I'm going to show you a picture of this function, but are there any questions about this? The reason these things are important ultimately is going to be for applications. You can model production and other types of scientific applications, economic applications. You can model them with functions. You can model the phenomena you see with functions, and it's very important to figure out where things are maximized. Like for instance, the cost to produce. If you have you have the volume, for instance, of a can, and you want to have a certain volume in a can, and you want to construct the can in a certain way so that you minimize the amount of material used. That becomes a maximum, or that becomes a minimum type problem, finding the minimum. Okay, now there's the function. I drew it there for you. Okay, I'm just going to let that ring. That's a telemarketer. So I've drawn our function from negative 1 to 4. And you can see, hold on. This is a negative 1, right? You can see at x equals negative 1, that's the absolute minimum. And at x equals 2, that's an absolute maximum. It's a local max also, but it's an absolute maximum. Okay. Okay, I'm just giving you a moment to copy down the graph, and then I'm going to ask you a question. But do you have any questions so far? Who's like quite comfortable with this? Maybe not quite comfortable, but who's reasonably comfortable? Okay, good. I'm getting some good feedback here. Thank you. Okay, so this x equals 2, at x equals 2, John's comfortable till the exam arrives. I understand. Well, that's why it's very important to everybody do their homework, so that, because then you'll be comfortable when the exam arrives. So x equals 2 is an absolute, the function has an absolute maximum at x equals 2 and a local maximum at x equals 2 also. But at x equals -1, the function, it does have, at x equals -1, the function does have a absolute minimum, but at x equals -1, does the function have a local minimum? Does it have a local minimum? No, that's right, Lynn, it does not. Because in order to have a local minimum, you would need to have this part of the function. Okay, and I'm not saying the function does that, but you would need to know that the domain of the function would have to include that blue part there. And actually, let me just see one thing here. One moment. But in fact, you see, the function doesn't do that. The function actually keeps going down, so it doesn't do that. So that's why you can't say, just because you have an absolute minimum, that it is a local minimum. And you can't say, if you have an absolute maximum, that it's also a local maximum. In order to say you have a local maximum at a point, at an x value, you need to have the function defined, the domain defined, such that such that you have an interval around that point. Okay, so all right, and the book reinforces these concepts with definitions, and that's fine. But I think it's nice. How many kind of like having this intuitive feel? I like it. How many of you like it? Okay, but Sue likes it, and Lynn likes it. Good, good, good. All right. Notice, by the way, what I have here in terms of notation. This just means, for my TI-84, the x, like the window, -1 was the minimum value I used, 4 was the maximum value, and I had an x scale of 1. And then for the y-axis on my TI-84 calculator, I had -1 as y min, 2 as y max, and y scale is 1. So this is very common notation that's used. All right. Well, so we've learned certainly how to locate maximum and minimum values of functions, and what we want to do is use that to help us actually graph functions. Okay, so what I want to do, let me stop, and that's what section 4.3 is about. So let me stop the recording.